Hey there, it's Shannon Magic Myers, and today we'll be checking out Stokes' theorem. So let's warm it up by considering the vector field quantity negative y plus z times I plus quantity x minus z times j plus quantity x minus y times k, and the surface z is 9 minus x squared minus y squared, where z is greater than or equal to 0. So first of all, let's kind of get a picture of that surface that we're dealing with. If z was 0, do you see that we would have a circle with radius 3? So I'll put that down for our base. And let's take a look at the circle. And then z would be up here at a max of 9. So our surface would look, something along these lines. Of course, I'm not making the very most pretty surface, but you get the idea. Okay, that's why I teach math. I'm not an artist. Okay, so now let's take a look. So here on the circle, we have our line integral in a positive direction, so it's counterclockwise. And so this c, right, the boundary, is going to be, like we mentioned, x squared plus y squared equals 9. And then if we look at our surface here, we've drawn it out as 9 minus x squared minus y squared, z greater than or equal to 0. And then our vector field, if we take a look at, and then I'll just label our M, N, P. Considering z equal to 0, that gives us not the surface portion, but just the line integral portion, so the part that I wrote in purple. So our vector field in terms of x, y, and 0 would just be negative y times I plus x times j. And there would not be a k component. It would zero out. And so the line integral over that circular boundary of this vector field f dot dr will be equivalent to the line integral of f, I'm going to put it into differential form, dot dr dt times dt. And that in turn will be the integral over c of m dx plus n dy. And this will give us the integral over our boundary of negative y dx plus x dy. Cool so far? Our line integral. So let's go over here, and I want to put this into, so x will be equal to 3 cosine t, dx will be negative 3 times sine at t, dt. Y will be 3 sine t, and dy will be 3 times cosine t dt. And we're going a complete circle, so we'll be going from 0 to 2 pi. So this will give us the integral from 0 to 2 pi of negative y dx will give us negative 3 sine at t times negative 3 sine at t dt. And then x was 3 cosine t. And then dy is 3 cosine t dt. So it looks kind of mean, but we'll actually get 9 times sine squared at t plus 9 times cosine squared at t dt. Well, when you factor out the 9, you just get 1 for sine squared of t plus cosine squared of t. And so this will bring us over to the integral from 0 to 2 pi of 9 dt, which of course will be 9 pi. Cool so far? Don't worry, there's an evil plan to this. All right, now looking at the surface integral, right, and we've got curl f dot n, that dot product, where n is the normal vector. We're gonna see what this is equivalent to. All right, so the curl of f is equal to the determinant if you've got I, j, and k. And we are looking at we'll have the first partial with respect to x, the first partial with respect to y, first partial with respect to z, and then we'll have our vector field information here. And so that is negative y plus z for my m. My n is x minus z, and my p is x minus y. So I need to find the determinant of all that. And so that is equal to, if I expand across ijk, I will have x minus z times the first partial with respect to x, and then, or not times, actually, let's write this. That will equal to, if I expand about ij and k, the first partial with respect to y of x minus y, it'll be a quantity here, minus the first partial with respect to z of x minus z. All of that will be times I. And then minus, now I expand about j, we'll have the first partial with respect to x of x minus z minus the first partial with respect to z of negative y plus z. All of that's going to be times j, and then plus the first partial with respect to x of x minus z minus the first partial with respect to y of negative y plus z. All of that times k. And this in turn will be, let's see, we'll get negative 1 minus negative 1 times I minus 1 minus 1 times j, and then 1 minus negative 1 times k. And so, let's see, the first two 0 out, so we just get 2 times k, and that's the curl of f. Good so far? All right, on to the next part. So now we need to find the surface integral. So the surface integral of the curl of f dot n with respect to the surface is going to end up being, is going to be equivalent to the double integral over the region. You've got your height 2 times dA. And the reason I'm doing this is because we already know that the base is a circle. And so we will just end up getting 2 times the area of the circle, which of course is going to be 2 times pi times r, which is 3 squared, which is 18 pi. And check it out. We got 18 pi here, and we should have gotten 18 pi here. I'll fix that. This should have been 18 pi. That's what you get for not writing out the integral. It would have been 9 times 2 pi minus 9 times 0. So they are equivalent. Awesome. All right, so what does that mean? That means that it turns out the line integral about the boundary of f dot dr is equivalent to the surface integral of the curl of f dot n with respect to the surface. Cool? All right, so guess what? We just did Stokes' theorem. We just verified Stokes' theorem. So now let's kind of just get into the description here of what we have going on. Stokes' theorem gives the relationship between a surface integral over an oriented surface S and a line integral along a closed space curve C, forming the boundary of S. And then we've got, let's just sketch out the plane here. Okay, that's the first quadrant of the XY plane, or the first octant. So we will take a look at you have some kind of surface going on, right? So let's just say, I don't know, we have a surface like we did on that last one, right? So we had some kind of parabolic surface. And we had that region, that boundary of the surface. By the way, it doesn't have to be circular, just doing that to make it easy. And then of course, this is 3D. And then what happens is, if you kind of map it down into the plane down here, right, you can take a look at that circular region. And that is your R. Cool so far? All right, so, and this, of course, has that positive orientation counterclockwise. Cool? All right, and then you have a normal vector coming up here. And something like this. Groovy? All right, so Stokes' theorem basically says you've got S is an oriented surface with unit normal vector n, bounded by some piecewise smooth simple closed curve C with a positive orientation. If F is a vector field whose component functions have continuous first partial derivatives on an open region containing S and C, then it turns out that the line integral over the boundary of the surface, C, of f dot dr is equivalent to the surface integral over the oriented surface S of the curl of f dot n with respect to that oriented surface. Groovy? Okay, so the first example, we're going to use Stokes' theorem. And just to let you know, we verified Stokes' theorem in our warm-up. All right? So there are some problems asking to verify, etc. So that is an example of how one would verify. We are now going to use Stokes' theorem to evaluate the integral f dot dr, and that, should have a C, where the vector field f is equal to z squared times I plus 2x times j plus y squared times k. And our oriented surface is z equals 1 minus x squared minus y squared, where z is greater than or equal to 0. Groovy? So here we go. We now have, we have something kind of similar to what we were working with over here, right? We have a circular base. And so let's take a look at, we know we have to find the curl of f, right? So the curl of f will equal to the determinant, put that C higher, of ijk, and then we're going to have the first partial with respect to x, first partial with respect to y, first partial with respect to z, and then this is our m, n, and p. So we'll have z squared, 2x, and y squared. Okay, so this curl is equal to, again, I'll expand across ij and k. So we will end up having the first partial with respect to y of y squared minus the first partial with respect to z of 2x times I minus quantity first partial with respect to x of 2x minus first partial with respect to z of z squared all times j, and then plus the first partial with respect to x of 2x. There we go. I see a error here. Sorry, my bad. We should have been using this guy and this guy when we were finding that corresponding determinant. So this would be y squared. And then the first partial with respect to x of 2x times first partial with respect to y of z squared. And that is times k. All right, so let's see what we get. We'll get 2y times I minus, this is 0 minus 2z, so minus negative 2z times j, and then plus 2k, which of course is 2y I plus 2zj plus 2k. Good so far? Awesome. All right, now z, so that's kind of part one. So now z was equal to, this was from our oriented surface, 1 minus x squared minus y squared, right? And the first partial with, so here, let's rename that as capital G of x and y is equal to 1 minus x squared minus y squared. And so gx will be negative 2x, gy will be negative 2y, z will be 0, and so dz is 0. And if you recall, an upward normal vector can be found by negative gx of x and y times I, and that's a negative, and then minus gy of x and y times j plus k. That's upward normal. So using that formula, the negative gx of x and y, this was a lowercase in the general, here we've got an uppercase, we'll end up getting our n equal to negative 2x is positive 2x times I, negative 2y is plus 2y times j, and then plus k. And so when we find the dot product, we'll have the curl of f dot n would be equal to 2y I plus 2z j plus 2k dot 2xi equal to 4xy plus 4yz plus 2k, nope, just 2. But we know what z is, right? So if we plug in z, we'll have z was 1 minus x squared minus y squared. And then don't forget, we still have plus 2 hanging about, which gives us 4xy plus 4y minus 4x squared y minus 4y cubed, and then plus 2. Awesome. So now we just need to find the integral, right? So, or the surface integral, sorry. So here we go. We have all the prep done for it. So the surface integral, or over that oriented surface S of curl F dot N ds will equal to the double integral over the region of that dot product with respect to the area over that xy plane. And then that's going to be, we have 4xy plus 4y minus 4x squared y minus 4y cubed plus 2. Now, that area is going to be, remember, it's a circular area, right? Because when z is 0, so the base, so when z is 0, we have x squared plus y squared is 1. And we know z is between 0 and 9 inclusive, all right? So we will have the integral from negative 1 to 1, and then the integral of negative root 1 minus x squared to root 1 minus x squared. And then all of this stuff, 4xy plus 4y minus 4x squared y minus 4y cubed plus 2 dy dx. And then that will be the integral from negative 1 to 1 of 2xy squared plus 2y squared minus 2x squared y squared minus y to the 4th, just integrating here, plus 2y. And that's evaluated from y equals root 1 negative root 1 minus x squared to y equals positive root 1 minus x squared. And then we'll have integral from negative 1 to 1 of. So 2 times x, y squared is just going to be 1 minus x squared, that quantity, plus 2 times 1 minus y squared minus 2x squared times 1 minus x squared. Again, you square a square root and it goes away. Now we'll have minus the quantity 1 minus x squared squared, because you're raising y to the 4th, and then plus 2 times root 1 minus x squared. Minus, so this is all still in the same integral. Now look what happens when you raise a negative to an even power. Will end up, the negative will go away. So we're going to end up with almost the same thing. So a lot's going to zero out. And my apologies, this should have been an x. except for this one, the negative won't go away. Good so far? And then we bounded the whole thing. So all of this is going to zero out because this minus will flip the signs, except for the very last one. So you're going to end up getting the integral from negative 1 to 1 of 4 times root 1 minus x squared. And all of this, sorry, was with respect to x because it was still in the integral. Excellent. All right. And then, so we could do this next integral with trig substitution. But if we look at this definite integral right here, inside the integrand, once we take that 4 out, if you think about it, it's just the top half, or no, sorry, you're going, top half of a semicircle, right? If you were to draw it out. And so you just have this region here, and this here would be 1. And so you'd have a semicircle with radius of 1. So the area of the semicircle of radius 1 would be 1/2 pi times 1 squared, which would be pi over 2. So this would be equivalent to 4 times pi over 2, which is just 2 pi. Cool? Awesome sauce. All right. Yeah, when you can do an integral using a known region, that's super awesome. I actually, when I was working out the key for this, did it with trig substitution, and it was a bummer. All right. Not that bad, but just extra layer. All right. So now, physical interpretation of curl. So if you take a look, I've made this disc, okay, and the name of this disc is S alpha. So it's disc S alpha. And then this disc is oriented in a positive direction, and it has a center at XYZ, and it has a radius of alpha. Good so far? Okay, now so let me fill in what we've got going here. So in a vector field F, we're letting S alpha be a small circular disk of radius alpha centered at X, Y, and Z. We drew all that in already. And with boundary C alpha. So C alpha was our boundary. So at each point on the circle, C alpha, this vector field F has a normal component, F dot n, and a tangential component, F dot t. The more closely that F and T are aligned, the greater the value of F dot T. So a fluid tends to move along the circle, which is important, rather than across it. So the line integral around C alpha measures the circulation of the vector field around the boundary C alpha. So let's take a look. I mean, you might have been noticing that with Stokes' theorem, the idea behind it, it's basically a 3D, a generalization of Green's theorem from circulation in a planar region to circulation along a surface. And the cool thing here is that the surface itself, it doesn't have to be oriented upright. It can be any orientation, and which is very, very cool. I mean, if you look here at the official theorem, the only need that we have is that we find that normal vector n, and it's bounded by some piecewise smooth simple closed curve C. Now that orientation of the piecewise smooth simple closed curve C is positive. Okay. All right. So here we go. This is giving us the line integral around this C alpha F dot T ds. S is lowercase because it's going to be like arcs, right? That's going to give us the circulation of F around the boundary C alpha. So now I've taken this disk, and actually there's more going on, with this disk. Let's draw in F and N and F dot N and all that stuff, all right? So if we take a look at some point on the circle, right? And then we would have our vector field. So our vector field is maybe something like this at this point, right? So that'll be F at X, Y, and Z with this other, just this X1, Y1, Z1 maybe. And then we have our tangential component. So then we would have this something like this would be our T. And then if we just sort of draw some visuals here, what we have going on, all right, is this portion right here, okay, is the dot product of F and T. And so that's the length right there. And then if we have our normal vector, right, be coming out like this. So when we're looking at these tangential and normal components, this is what we're talking about here and here, right? So now let's take a look at the disk in terms of being on the surface itself, right? So again, you've got your same stuff that we have here, but you've got this big surface S. So this whole surface here is S. It's surface above the boundary line. Our boundary, our general, and then we're looking at just the boundary line of our circle right here, which remember has a positive orientation, right? And again, just like before, you've got your X, Y, and Z is the center point. And the little surface in here, this surface here is S alpha. And now if we think about the vectors sticking straight out, right? I'll do this. Hopefully these will show up well. You've got your curl of F, and then your normal vector. So your curl of F maybe is something like this. And then your normal vector is maybe something like this. Cool? And you could have like a bunch of these little tiny discs within the surface. Groovy? All right, so let's, put down the wording for this. Now consider a small disk as alpha to be centered at some point X, Y, and Z on the surface S. On such a small disk, the curl F is nearly constant because it varies little from its value at X, Y, and Z. Remember, this is like a little teeny tiny disk, and so it's not going to be that much different, and that it's not going to be that much different than that vector, that original vector field that evaluated at X, Y, and Z, which was the F from the original. Now, moreover, the dot product of curl F and N is also nearly constant on the little disk as alpha because all unit normals to S alpha are going to be about the same. Therefore, Stokes' theorem yields the line integral with the boundary C alpha of F dot T, remember T is the tangential component, ds, is equal to the surface integral of S alpha, the oriented surface S alpha of the curl of F dot N, and then with respect to the oriented surface. Cool? Now that, in turn, remember how we said that dot product would be constant, some kind of constant? So we would have, and it would also, so it would be nearly constant on, any curl that we would do times any normal on that little tiny disk is nearly constant. So we would get curl f dot n and then times the surface integral of the oriented surface S alpha with respect to ds, where S is that big surface, right? And that in turn is going to be the curl f dot n. Well, what did we pick? We picked a circular boundary, didn't we? And the radius was alpha, so that would be times pi alpha squared. And so the curl of f dot n will equal to the line integral with the boundary C alpha divided by the area of the region enclosed by C alpha, which was pi alpha squared. And that, my friends, is the rate of circulation. Pretty cool. All right. So assuming conditions are such that the approximation improves for smaller and smaller disks, so alpha approaches 0, it follows that the curl of f dot n is equal to the limit as alpha approaches 0 of 1 over pi alpha squared times the integral over C alpha, our line integral, f dot t, so the vector field times that tangential component of f ds. And that's referred to the rotation of f about n. Cool, cool? All right, in this case, the rotation of f is maximum when the curl of f and n have the same direction. Normally, this tendency to rotate will vary from point to point on the surface S. And Stokes' theorem, the line integral of that curl f dot n ds, which is the surface integral, equal to the line integral of f dot dr. That's our line integral. It says that the collective measure of this rotational tendency taken over the entire surface S, surface integral, is equal to the tendency of a fluid to circulate around the boundary C, which is that line integral. So this one is the surface integral, and this one here is our line integral. Okay, so let's look at our second example. The motion of a liquid in a cylindrical container of radius 1, so cylindrical container of radius 1, is described. So what does that tell us? Beautiful. That tells us that S is going to be x squared plus y squared is 1. The motion of this liquid in the cylindrical container of radius 1 is described by the velocity field f at xyz is negative zi plus yk. We want to find the surface integral of that oriented surface of curl f dot n ds, where s is the upper surface of the cylindrical container. So, well, maybe we need to find the curl, or f, right? So curl of f will be equal to, again, this is the easiest way to remember it, I, j, and k. This is m and p, because j is zeroed out. And so first partial with respect to x, first partial with respect to y, first partial with respect to z. And then we have negative z, 0, and y. I know it would be nice to expand about the 0, but sometimes with the curl, I think it's just easier to go about I, j, and k. So we'll have first partial with respect to y of y. The next one will zero out, right? Because it's going to be 0. And then we'll have times I. And then minus. Now going about j, we'll have first partial with respect to x of y minus first partial with respect to z of negative z, and that'll be times j, and then plus first partial with respect to x of 0, zero's out, minus first partial with respect to y of negative z, that will also zero out, all of that times k. So this will give us I plus j. Oh, sorry, 3 minuses. So we'll have I minus j. And then 0k. And so remembering that one formula, right? Where was it? Up here, upward normal vector. If we find that the first partials with respect to x and with respect to y of I and j, I mean, that's going to be, we're not going to get anything, right, from this field. And so we're just going to let n equal to k because the other parts zero out. Because there's no x coefficient to the I, there's no j at all. Cool, cool? All right. And so the curl of f dot k, which is our n, will be equal to I minus j dot k, which is going to equal to 0. And evaluating the surface integral of 0 is just going to be 0. So at the end of the day, the surface integral of that oriented surface of the curl f dot n ds equals 0. And we're done. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that subscribe button and like the video. Thank you. Bye.